So we now move on to the topic of frequency domain interpretation of continuous signals and systems, which is again something that has been covered in the previous class. We'll go over it quickly. We understand what LTI systems do to the inputs in time. In time, they are convolving the input with the impulse response and giving us the output. But it is not very intuitive for us to understand what is the meaning of that convolution. What are LTI systems really doing to my input signal? If I have an LTI system with certain impulse response, let's say I record some speech and I pass it through that LTI system, what is it going to do to my speech? So to do that, it is good to look at signals and systems in some transform domain. So mathematically, you can rigorously define what is a transform. Right now, I'll just take an intuitive answer to this question of what is a transform. And a transform is just another way looking at a mathematical function. The function could be the impulse response, the function could be an input, the function could be an output. Right? It is like you are looking at the same thing, but now looking at it in a different light. So, for example, you could have a specimen, a biological specimen, and you can look at it visually, or you could use a microscope to magnify it, or you could do some other way, you could use some other instrument to take a look at that biological specimen. It's the same thing. But why do you want to look at it in a different fashion? Because it will give you certain different information that you had previously available about it. So if there is a time domain signal, we know what it looks like, but it doesn't really give us that good of an intuition. What is that signal really about? So we want to look at it in a transform domain to give us better insight into the signal. Now, what are transforms good for? I know you guys have learned about a lot of transforms, and sometimes people just go about these transforms without really realizing why are we learning all these transforms, what is their purpose. So I'm going to give you just a 1-minute description of what are transforms good for. So one good use that they have is for analysis. They simplify certain types of analysis. Okay? And the best known example of these kinds of transforms is the Laplace transform. Laplace transform, the biggest advantage of that is that it helps us solve differential equations very easily. Okay. While solving differential equations in time is really difficult, if you use Laplace transform, it makes your life much easier. So that is one key advantage of Laplace transform. So some transforms are really good because they simplify analysis. Now, the second thing that transforms provide, in addition to simplification, is they provide insights into the nature of signals and systems. And not all transforms provide that, but we have many transforms that do. In the context of these classes, or in the context of electrical engineering, the transform that provides us that understanding is called the Fourier transform. Why? Because the question is what domain. So if you are talking about a transform domain, what domain should we go to understand time domain signals? And the answer is the best counterpart for us humans is that time has an equivalent, a flip side of it, which is frequency. And Fourier transform helps us. Fourier transform is nothing but a frequency representation of your signals. So let's first intuitively understand how does Fourier transform tell us about the frequency of a signal or a system or whatnot. So let's address first what is a frequency. Because so frequency is the rate at which something changes. And as humans, we really understand the notion of frequency very well. Now, there are signals signals or functions that change at a fixed rate. Or fixed frequencies. So an example of that are sinusoidal signals. So let's say I have x of t, which is sine of 2 pi times 200t. Okay? We look at this signal and we know that this signal cycles at a rate of 200 cycles per second. Right? This is the frequency of the signal, 200 cycles per second, or we call 200 hertz is the frequency of the signal. If you plot it or if you look at it in 1 second, it will go through its ups and downs 200 times. Right? We can have a cosine based signal also, so I can have x of t, which is cosine of 2 pi, for example, 4000 t, and this is a signal which has a frequency of 4 kilohertz. It changes 4,000 times per second. I can have a complex signal also, which is e to the j 2 pi 8000 t, which is a phasor, which means that if I plot it in the 2D, in the complex plane, then it's going to complete 8,000 rotations per second. I can have a negative frequency associated with this. I can have e to the minus j 2 pi 8000 t, which means that this phasor, instead of turning right, will turn left 8,000 times per second. Right? So there are signals which we really know have a fixed frequency. What does it mean to have a Fourier transform of a signal which is not one of these sines or cosines or complex sinusoids? Right? So for that, we'll look at the transform. The right transform for that is called the continuous time Fourier transform, which is attributed to Joseph Fourier, and it's a name, that's why we don't write F in small letters. It's always capital F. It's the name. Now, what is the brilliance of Joseph Fourier? That he realized such a long time ago that even if a signal is any odd signal, any time domain signal, any x of t that has finite energy. So what does finite energy mean? That if I integrate it over all possible values squared dt, that is less than infinity. So any signal which has finite energy can be represented as a superposition of sinusoids. It's up to you whether you want to write them with sines, cosines, or complex exponentials. We'll work with complex sinusoids. It's like saying that just like, at the end of the day, all matter can be thought of as atoms. Right? It's atoms combined together to make matter. Fourier is saying that any signal which has finite energy is like built up of gazillions of sinusoids. Not one or two, but a large number of sinusoids. And this is really remarkable if you think about it. So, what Fourier is telling us is that we can write a signal in terms of a superposition of a large number of sinusoids, and then we can think about the frequencies present in that signal in terms of those sinusoids. So Fourier transform, or CTFT, continuous time Fourier transform, essentially tells us which frequencies make up the signal. Just like you can say this is water, or it's H2O. It has 2 atoms of hydrogen and 1 atom of oxygen. You can really look at a continuous time signal, compute its Fourier transform, and say that this signal has these many frequencies. It has frequencies at 2 kilohertz, 3 kilohertz, and so forth. Right? So, to illustrate that point, for example, let's go back to the example that of a signal which is just a pure sinusoid. So let's say I have x of t, which is 4 e to the j pi by 4 e to the j 2 pi 8000 t. Okay. I can write this as a e to the j 2 pi 8000 t. Now how do I read this statement? What it says is that x of t is a complex frequency. It's a frequency of, it's an 8 kilohertz frequency. Its amplitude is 4, so A is 4, and its phase is pi by 4. Right? This is how I read it. This signal is one sinusoid with amplitude 4 and phase pi by 4. I could have another signal like this. I could say I have x of t equals a e to the j 2 pi 8000 t plus b e to the j 2 pi 4000 t. And I can now say that I have a signal which is actually made up of 2 sinusoids. It has a sinusoid with frequency 8 kilohertz, and it has a sinusoid with frequency 4 kilohertz. Okay. So this is a sum of 2 sinusoids. Now, why does continuous time Fourier transform tell us about the frequencies. To do that, actually, we'll look at Fourier transform in the reverse way. Right, remember the inverse continuous time Fourier transform formula. So x of t has a Fourier transform x of j omega. Okay? So how do we write this inverse Fourier transform formula? We write x of t equals 1 over 2 pi minus infinity to infinity x of j omega, which is some complex number, e to the j omega t d omega. Okay. Now compare this x of t with this inverse Fourier transform formula. This x of t is saying that it is made up of two frequencies, so there is a summation. In a inverse continuous time Fourier transform formula, instead of summation, we have integration, which means it is made up of an infinite number of frequencies. And each frequency is given by, so here if I just call this as, let's call it omega 2. Let's call this 2 pi 8000 as omega 1. So here instead of e to the j omega 1 t, I'm writing e to the j omega t. So I have frequencies omega, which are now radians per second. So remember, radians per second is equal to 2 pi times hertz, right? So 2 pi times 4000, that's 8000 pi radians per second. So my omega is going from minus infinity to infinity. E to the j omega t is the omega is the frequency of my sinusoid, and what is the amplitude and phase of my sinusoid? That is given by the Fourier transform. So how much omega frequency is present in x of t? That, to find that out, we have to look at x of j omega. So x of j omega can be written as magnitude and phase. Okay. So this is the magnitude of that frequency and this is the phase of that frequency. So if someone asks you, you are given a signal which has some Fourier transform x j of omega, and they say, does that signal have the 4 kilohertz frequency present in it or not? What does that mean? To find out whether that has 4 kilohertz present or not, you evaluate the Fourier transform at omega equal to 2 pi times 4000, right, or 8000 pi. So you compute x of j 8000 pi. Right? If this is 0, then this means that x of t has no 4 kilohertz component in it. Okay? So when we look at it, what is the true meaning of Fourier transform? The true meaning of Fourier transform is when you calculate the Fourier transform of a continuous time signal, which has this formula, that how do you compute x of j omega? The Fourier transform formula is this. You do minus infinity to infinity x of t e to the minus j capital omega t d omega. When you compute this, you are effectively computing the components of the signal that correspond to frequencies omega. You look at xj of omega, and every capital omega tells you how much omega frequency is present in your signal. Okay? So Fourier transform gives a view about the frequencies about the frequency view of the signal. So this should have been dt. So a brief recap of the Fourier transform in terms of what it tells us is the following, that if x of t is finite energy, then there exists a Fourier transform of the signal which is given by the above formula. It's called the continuous time Fourier transform, and what this Fourier transform tells us is the frequencies that make up your finite energy signal. So when you write your signal in terms of the inverse Fourier transform, x of t equals to 1 over 2 pi minus infinity to infinity x of j omega e to the j omega t d omega. This equation clarifies that your signal is made up of an infinite number of frequencies with frequency e to the j omega t, and the phase and amplitude of the frequency is given by the Fourier transform x of j omega. So if you take the classical example of just a pure sinusoid, so let's say your x of t is equal to 2 cosine of 2 pi 1000 t. So this is a sinusoid with a frequency of 1 kilohertz. It's a cosine, and the Fourier transform of this thing is x of j omega equals 2 pi delta omega minus 2 pi times 1000 plus 2 pi delta omega plus 2 pi times 1000. Now if we think of them in terms of a plot in the frequency domain, omega domain, then what that means is we have two impulses, one at 2 pi times 1000 radians per second and the other at minus 2 pi times 1000 radians per second, and the area under these impulses is 2 pi for both of these impulses. Now why does this cosine give us two impulses? The intuitive way of thinking of this is using the Euler's identity, where a cosine with 1 kilohertz is effectively made up of a positive 1 kilohertz frequency and a minus 1 kilohertz frequency. What the 1 kilohertz frequency says is that you have a phasor which is rotating in the clockwise direction at the rate of 1000 rotations per second, and the minus 1 kilohertz frequency is that it's a phasor which is rotating in the anti-clockwise direction at a rate of 1000 rotations per second, and the cosine is the sum of these two frequencies. So it's a pure sinusoidal signal which is made up of two frequencies, so we get two impulses. So pure sinusoids always exist in the Fourier transform as impulses. So as another example, if I had, these are simple examples, if I had another signal with 2 cosine of, let's say, 2 pi 1000 t plus 3 cosine of 2 pi 2000 t. Now I have two cosines in the signal. Using the Euler's identity, I have effectively a plus 1 kilohertz frequency, minus 1 kilohertz frequency. This is plus 2 kilohertz and minus 2 kilohertz. Now I can of course calculate the Fourier transform of that. If you remember your formula, that will be just a generalization of this. It will be 2 pi delta of omega minus 2 pi 1000 t 1000 plus 2 pi delta of omega plus 2 pi 1000. That will be due to the first cosine plus 3 pi delta of omega minus 2 pi 2000 plus 3 pi delta of omega plus 2 pi 2000. But in general, you should just intuitively know that this signal has now 4 frequencies, and you should get a Fourier transform which will have an impulse at 1 kilohertz. It will have an impulse at 2 kilohertz. And similarly, it will have an impulse at -1 kilohertz and -2 kilohertz. And the area of these impulses will be a function of the power of your signal. Now, that is the essence of the Fourier transform. That continuous time Fourier transform tells us about the frequencies present in the signal. So if I have here is another example. If I have a signal x of j omega, which I prefer to draw because pictorially you can get a better sense, but of course you need to be able to relate the diagrams with the mathematical equation. Let's say my x of j omega is something like this. And this is, let's say, 4 pi times 100. And this is -4 pi times 100. So this is 200 hertz, this is -200 hertz. Now previously we were looking at pure sinusoids, so we had impulses. Now we don't have any impulses. So one thing that formula, I could write the formula for that too, but one thing this picture or formula tells us is that the signal doesn't have any pure sinusoids. But another thing that this Fourier transform is telling us is the signal has no frequencies above 200 hertz because everything after 200 hertz and -200 hertz or before -200 hertz is 0. So the signal has no frequencies beyond these points, which means that the signal is not changing very fast. It's a signal which doesn't vary that fast. Because what is higher frequencies? The signal is changing too fast. Okay? So now let's move on to the question of this is what the Fourier transform tells us about signals. What does the Fourier transform, the continuous time Fourier transform, tell us about systems? Now to understand that, we have to remember two things. Number one is that every LTI system is fully described by an impulse response. Let's call that h of t. So if we know the impulse response, we know the output to every possible input. And the second is that assuming that the impulse response is finite energy, which means that assuming the integration squared of h of t is less than infinity, we know that the impulse response will have a Fourier transform, so we can figure out the frequencies present in h of t. How do we figure that out? We simply take the Fourier transform of h of t. When we compute the Fourier transform of h of t, we get h of j omega. And when we look at h of j omega, we know which frequencies are present in h of t. Now, what do the frequencies in h of t, or equivalently h of j omega, tell us about the behavior of the system on inputs? So Fourier transform of a signal tells us which frequencies are present, but what does the Fourier transform of the impulse response tell us in terms of the system? What is the system doing on the signal? Now, to do that, we have to remember the convolution property of the continuous time Fourier transform. So the output of a system, if this is our system, the impulse response is h of t, input is x of t, output is y of t, then we know that y of t is x of t convolved with h of t. What's the Fourier transform of the output? The Fourier transform of the output is y of j omega. By convolution property, we know that convolution in time is multiplication in frequency. So we get x of j omega multiplied by h of j omega. Now, what is y of j omega? Y of j omega is frequencies in the output of the system. So if you look at this relationship, what we see is that the frequencies that are in the output are related to the frequencies that are in the input signal times the frequencies that are present in the impulse response. Right? So if I say, for example, I want to find out what or how much frequency, what is the magnitude and phase of 3 kilohertz frequency in the output. So what does that mean? That means that I am interested in finding out what is yj 2 pi times 3000. Right? That's 3 kilohertz. So I am interested in calculating yj 2 pi 3000. By the formula, that is equal to x times j 2 pi 3000 times h j 2 pi 3000. So what is that saying? The frequency, output frequency at 3 kilohertz is equal to whatever was the frequency present in the input signal at 3 kilohertz times whatever is the frequency of the impulse response at 3 kilohertz. So the input-output relation is simply given by you multiply your input frequencies with the frequencies of your impulse response. It's just a multiplication operation, and what it says is there are 3 or 4 basic lessons that we can derive from what does LTI system do on inputs. Instead of using a specific value of frequency, I'm going to use omega, just a variable for. So use omega for an arbitrary frequency. So here are the lessons that we can draw. Number one thing is, if x of j omega equals to 0 for omega, then what does it mean for the output frequency? So if my input frequency, what does it mean x of j omega equal to 0? It means that at frequency omega, the signal has no frequency. Right? The previous example that we saw, the signal had no frequency above 200 hertz. Now, if the input signal does not have a frequency at omega, using the convolution property formula, what will be y of j omega? So if x of j omega equals to 0, y of j omega will be equal to 0. Now what does that tell us about the function of LTI system? This means that LTI systems cannot add new frequencies to input signals. If an input signal had no frequency present, an LTI system cannot add that frequency into the output signal. If, let's say, I am singing and I have no note above maybe 2 kilohertz. No matter what kind of LTI processing I do, I cannot regenerate an output which will have a note above 2 kilohertz. Now, the other thing is that let's look at just the amplitude of the output frequency. So remember, y of the amplitude of output frequency, forgetting about the phase, that is equal to x of j omega times h of j omega. So it means that, let's say, my input frequency had, at some omega, had a scale of, let's say, 10. By designing an appropriate impulse response, by designing an appropriate h of j omega, I can either scale up that frequency or scale down, because it's just a multiplication operator. So LTI systems can either scale up, increase, or scale down just decrease the frequencies that are present in an input signal. For example, let's say that your input signal had a frequency at 2 kilohertz, and you want to make it, at the output, you want to make sure that you have no frequency at 2 kilohertz. What's the easiest way to do that? You design an impulse response so that h of j omega is 0 at 2 kilohertz. Since you are multiplying your output frequency with input frequency times the impulse response frequency, if h of j omega is equal to 0, then your y of j omega will be equal to 0. But in general, you can scale it up and down. Right? So if an input frequency is present in the signal, you can either increase the contribution of that signal or decrease the contribution of that signal. That's effectively what is, for example, changing the bass or treble in a song is. You are increasing or decreasing the input frequencies. Also, if we write down the phase of the output frequency of the output, so the phase, of course, adds up. That follows by writing the formula in the polar form, right? Now, this means that LTI systems can change the phase of the input frequencies. The fourth point, which I sort of alluded to in the second point, is that if x of j omega is not equal to 0 for some omega, but h of j omega equals to 0, then this will mean that y of j omega equals to 0. In other words, LTI systems can kill frequencies. So the frequency domain interpretation, the continuous time Fourier transform, for when we apply it to the LTI system, that tells us 3 or 4 major things about LTI systems. Number one, LTI systems cannot add new frequencies into the system. Number two, LTI systems cannot add any new frequencies to the input signal. Number two, LTI systems can eliminate frequencies in the input system. Right? Number three, LTI systems can increase or decrease the contribution of frequencies in the input signal. And number four, they can change the phase of the input frequencies. And effectively, an equalizer, which I'm sure you have seen in all kinds of music settings, is nothing but an LTI system. So if you look at, for example, a general equalizer, it has these knobs, whether you are looking at it in the digital domain or whether you are looking at it with a manual setting, right? And these numbers are basically, in general, just telling you the usual, what's the mid-range of the frequency. So this is like 20 hertz, 25 hertz, 31 hertz, all the way up to 20 kilohertz. We don't go above 20 kilohertz because human ear cannot typically distinguish above 20 kilohertz sound anyways. And what are these scales doing? These scales are effectively saying, well, I like my music around these low frequencies to be a little bit less. I don't want these frequencies in my outputs, the music that I'm generating. So I bring down this part of my equalizer, which is now it is scaling down those frequencies. Right? If I had an equalizer where I could put it all the way down, then that's effectively killing that frequency. And actually, I like my frequencies around this region to be a little louder. Okay? So I increase that up. So if nothing else, using the LTI system theory, you can actually build an equalizer yourself in MATLAB or other program. Because an equalizer is doing nothing but implementing an LTI system. Okay? It's scaling down the frequencies, it's scaling up the frequencies, and if you can drive it really down, it can kill off some frequencies. But it cannot bring back the frequencies that were never in the input song to begin with. Okay? If your input song was recorded where it had no frequencies above 10 kilohertz, no matter what you do with your equalizer, it's not going to add 10 kilohertz or 15 kilohertz frequencies. Okay? So let's take a look at some of the most common names for LTI systems, which are given based upon what do the Fourier transform of their impulse response look like. So the idea is an LTI system has an impulse response h of t, and when we take the Fourier transform, it's h of j omega is the Fourier transform. And I'm going to only write h of j omega absolute value. I'm not going to focus on the phase. Okay? The properties of giving the names to LTI systems is primarily based upon, although you can make further distinctions, what does the magnitude of the Fourier transform of impulse response look like? So one of the most common versions is, if you plot it, it looks like this. minus omega c to omega c, 1. This is what it will look like. If you want to write it mathematically, it will look like 1 for absolute value of omega less than or equal to omega c, which is, omega c means a fixed number. It's not a variable anymore. So it, for example, omega c could be, let's say, 2 pi times 4,000 radians per second, and 0 otherwise. So this LTI system says that if you look at it, the system is going to let all the input frequencies up to omega c frequency pass without any change in scale, because the height is 1, right? So y of j omega is equal to x of j omega absolute value times h of j omega absolute value, which means that up to 4 kilohertz, it's going to let all the frequencies pass with no change in magnitude, and then what is it going to do? Outside the 4 kilohertz, it's going to kill off all the frequencies. This type of an LTI system is called a low-pass filter. Why is it called a low-pass filter? Because the idea is that it lets low frequencies pass and it lets all the high frequencies go to 0. It kills them off. This is an ideal low-pass filter. So this is one. Another type is if you plot the impulse response Fourier transform. Again, I'm just plotting the magnitude. Okay. So it looks like minus omega 2, minus omega 1, omega 1, omega 2. And the height can be, typically it's taken to be 1. What is this filter? This filter is saying that, or this LTI system, which we just call them filters, right? Because effectively they are just filtering the frequencies. This filter, for example, omega 1 could be 1 kilohertz, and omega 2 could be, let's take it to be 4 kilohertz also. Right? So this is saying it will let all the frequencies between 1 kilohertz and 4 kilohertz pass and kill off all the rest of the frequencies. This type of a filter is called a band pass filter. So a filter which lets frequencies in a band pass and let the other frequencies go to 0. The third common type is a filter whose Fourier transform looks like the following. And this keeps on going. So this could be, for example, this is still denoted by omega c. This is 2 pi 4,000, then the height is 1. Now this filter is the reverse of the low pass filter. What is this filter doing? It's killing all the frequencies between minus 4 to 4 kilohertz. So this filter is letting low frequencies go to 0 and letting the high frequencies pass. So this filter is called a high pass filter. So this is a filter which lets high frequencies pass, low frequencies get killed. It's the opposite of the low pass filter. Okay. And then just like the band pass filter, there is an opposite of that, which is a band stop filter. Yes. So a band stop filter will be the reverse of the band pass filter, it will be 1 from omega 1 to minus omega 1, and then 1 again after omega 2. And what this filter is doing is it is killing only frequencies in a band and letting all the other frequencies pass. Now, these are ideal filters where we are making their amplitude to be 1. You can change the amplitude to be 2 or 3, but they will still be called the same: high pass, low pass, band stop, band pass, and so forth. Okay. I'll do a quick example to demonstrate the effect of a band stop filter or a low pass filter on an input signal's frequencies, and then we'll probably do some more examples in recitations. So let's say that you have a signal x of t whose Fourier transform looks like the following. I can write it as a mathematical equation. Of course, this is just equation of a line, so I can write that very easily, but I just want to show it graphically to you. Okay. So this is, first of all, what does this figure tell me? That this is an input signal which has no frequencies above 1 kilohertz. This is a frequency signal up to 1 kilohertz. And then I pass it through a low pass filter. Now, low pass filter is often written as LPF with omega c equal to 2 pi times 500 radians per second. So sometimes you just said it's a low pass filter with this cutoff frequency. The term that is used is cutoff frequency, which means you can just draw it yourself, that h of j omega, if there is no phase information, then it's just an ideal low pass filter with 1 up to 2 pi times 500 radians per second. So this is a low pass filter that is going to cut all the frequencies above 500 hertz. So what will be the output frequencies? Y of j omega. Well, the answer is simple, that up to, so 500 hertz is exactly in the midway of this point. So this is 2 pi 500, and this is minus 2 pi 500. So this part is going to get multiplied by 1, which means we'll get back the same thing up to this point. The height is still 3. Now, after this part is getting multiplied by 0, which means that actually after this will go directly to 0. Okay. So this is 2 pi 500 minus 2 pi 500. And what will be the height here, where it will go exactly to 0? You can write the equation of the line, or you can just use the intuitive thing that you are halfway through, it's going from 3 to 0, so this should be 1.5.